YipuWang from USTC. I'd like to share my recent research about the using satellite microwave observation and light use efficiency model to estimate GPP of vegetation. Before that, I want to thank my supervisor, Professor Lee, and my co-authors. In this presentation, I like to mainly introduce this new model based on the EDVI developed by our group, and also show some validation results and comparison results with other satellite GPP products. So since our country proposed the carbon neutrality policies, studies related to the carbon and energy have gotten much more attention. Carbon sequestration is an essential part in this goal of carbon neutrality, and vegetation plays a key role in the carbon sequestration because vegetation absorbs the carbon dioxide from the atmosphere through photosynthesis, and which offset the CO2 emission, especially for the forest ecosystem, which is the largest carbon sink among the vegetation types. But there is still difficulty in accurate estimation of carbon storage or GPP in land ecosystems. For satellite remote sensing has greatly developed in recent years. By using different sensors on board a satellite, we can derive the GPP from local to regional and even global scales over different vegetation types. Generally, GPP can be accurately derived using the in situ measurements from flex towers at a local scale. But large errors can be introduced at large spatial scales. So satellite remote sensing provides us a powerful tool to derive GPP. Actually, there are many satellite GPP products have been produced successfully in recent years, but most of them are based on the satellite optic sensors. As Professor Lee and Dr. Fu introduced that, they cannot be available under cloudy sky, so which may introduce the uncertainty in studying vegetation and atmosphere interactions. Yeah, and there is a famous example, as Professor Lee introduced, that if the Amazon forest became green or not during the drought period in 2005, the two independent studies used the same index and even the same analysis method, but they got totally different conclusions. Why? Because they use the different data from even the same index from different versions, which has different cloud processing methods. There is a study comparing such difference, as we can see in the upper left figure. For the same MODIS LAI of version 4 and version 5, there we can see that there is a large discrepancies even for the same index, and such large differences result in the large different GPP estimation. So back to this slide, we can conclude that insufficient satellite observations may lead to our bias in studying some scientific questions. So yeah, compared with the optical sensors, microwave with longer wavelength can penetrate the can be less sensitive to the cloud change. I think this is very useful and important over the South China, where the cloud cover present quite frequently throughout a year. In addition, the microwave can penetrate the canopy layer. This can make them reflect the canopy dynamics under different sky. So I think this is one of the largest advantage. Our group has developed the new index EDVI. Professor Li and Mr. Fu has introduced, so I will skip the detail. I just mentioned several characteristics of this index. The first one is EDVI has a consistent seasonal, typically has a consistent seasonal variations with NDVI and LAI, but it is more sensitive to the short-term variations such as daily change in canopy water. The second one is that EDVI can be used to indicate the chronology of vegetation. The third one is that we have demonstrated that EDVI can be used to derive or estimate the transport water from vegetation. So we were thinking that if those characteristics can be used in the GPP estimation, because we know that the vegetation absorbs the CO2 at the cost of losing water. We first investigated the literature and found that there are very few studies which have used microwave data to derive GPP. And also from the perspective of satellite remote sensing, light use efficiency model, LUE briefly, is the most widely to derive GPP. So this study conducted a first attempt to combine satellite and microwave and LUE model to derive GPP. There is a logic of this model in this slide. Generally, GPP can be considered as a product of the maximum LUE and other stress factor, including the radiation, vegetation property, temperature, and water stress. Among these factors, vegetation index is often used to indicate the fraction of photosynthesis active radiation over vegetated surface. And for this factor, we think it can be quantified by the normalized EDVI. The other factors, water stress, can be indicated by the evapotranspiration. So in our previous studies, we have developed the transpiration method based on EDVI. So we think this method can be integrated into this model. For these two factors, I just mentioned 2 points. The one point is that NDVI and LAI is often used to derive FPAR from satellite remote sensing based on the linear or nonlinear relationship between them. Similarly, we think normalized EDVI can do the same thing. The second point is that water stress on GPP estimation, GPP generation can be variable under different cloudy sky. So in our previous study, we have derived the all sky evaporation method. So we think they can be also used for this. So to validate this model, we selected 7 sites over China. Here is 4 cases, 4 forest cases. The red color is the normalized EDVI, the blue color is the NDVI. So we can clearly see that over these 4 forests, normalized EDVAC has consistent and noticeable seasonal variations with in situ GPP measurements marked by black. This performance is also comparable to NDVI. So this means normalized EDVAC can indicate the seasonal dynamics of biomass, but differently, the short-term variations in GPP can be also, such as the daily variation or daily fluctuation, can be also captured by normalized EDVI. So we think this is one of its characteristics. More importantly, we found that the GPP correlated better with normalized EDVI with the increased clouds, particularly under overcast sky, better than other optic indices. This suggests that the microwave indices may be better able to capture the dynamics of GPP under clouds. Then we based these different indices, we derived the FPAR and compare it with the in situ GPP. So figure A is the comparison with EDVI-based FPAR and the GPP. And from the R square and the slope of the fitting line, we can see that the GPP correlates more with EDVI-based FPAR better than other indices. So this means microwave-based FPAR may be a better correlated GPP, but this needs to be more validated by in situ measurements. So based on this finding, we derived the GPP at the daily scale. So and compare it with the global satellite MODIS GPP and the ECLU GPP. Here shows the 7 time series of several GPP over 7 sites. Generally, the EDVI-based GPP estimation perform overall well with the in situ GPP. So this can be seen from this bar plots, the statistical metrics. But differently, we find that the optic based GPP products are severely or are overestimated at the evergreen forests during this transient period, which can be attributed to the saturation of optic signals. And also, we find that all of 3 models are severely underestimated over the croplands. We think this resulted from the different parameters and model structures. And this scatter plot shows a statistical comparison among the 3 models. The first row is the EDVI GPP and the in situ GPP. So we can see from the R square and bias, EDVI GPP perform overall better than MODIS GPP and ECL GPP at this 7 sites. But also we notice that due to the underestimation at the cropland sites, the 3 models shows some dropping scatters noticeably. So, but this also suggests that current satellite model need to be improved over the crop types. More importantly, our model can be used for different cloudy sky conditions. So we validated this point. The figure A shows the comparison with our estimation and observations. It can be seen that the two GPP has a consistent changing trend from clear sky to overcast sky, with the overall small fires as shown in figure C. The statistical metrics showing in below three figures also shows that the model performed overall stably and also overall well for the GPP estimation on the different sky. So these results demonstrated that the model may be feasible for the GPP estimation under dynamic cloud conditions. Finally, several uncertainties should be mentioned. They are from two aspects. One is that EDVI has its own uncertainty, mainly its coarse spatial resolution, which limits its application at small spatial scales. The second one is that the model structures maybe have some uncertainty. In current model, we did not explicitly consider the diffuse radiation effect on GPP generation. So some parameters also need to be optimized in the future work. Summary. So this study conducted the first attempt to derive GPP, combine microwave observation and LU model. So maybe we'll extend it to the regional or global scales in the future. Beyond this, in the direction of my study, we in these 2 years we have made some progress. We have published five papers about the carbon and water fluxes, and also now we have 2 papers under review. We have another 3 to be submitted to the end of the year or the next year. Thank you for your attention. If you are interested, you can email me or we can have a happy discussion.